Hope everyone's having a good spring break. I wanted to do a problem that was similar to the kinds that we'll be doing on the test on Tuesday. This is a circuit simplification problem. I've got a rather complicated circuit in front of you here. Consists of 8 resistors. And what we're going to do is we're going to simplify it, and then we're going to figure out how much voltage and current and power is going through or being dissipated by each of the resistors. So first thing you have to do is simplify the circuit down to one resistor, and you remember the rules are you simplify everything that's in series and then everything that's in parallel, and you keep repeating that until you're down to one resistor. Well, the first resistors we have that appear in series are 1 and 2 there. It's a 5 ohm resistor and a 3 ohm resistor. Since they're in series, I can just add them up algebraically. That works out to 8 ohms, and I call it R12 just because I'll need that designation a little later for something. There's another one that's in series, R6 and R7, so I just add those. That's R6, 7 is now 30, and that's all that are strictly in series. There are some that are in parallel. That's step 2. Well, R3, 4, 5, a 6, a 12, and a 4 ohm resistor. Remember, when they're in parallel, it's 1 over 6 plus 1 over 12 plus 1 over 4. You find a common denominator for that, which would be 24. You add them all up, and then you flip them upside down, and you end up with the equivalent resistance is 2 ohms, and I've labeled that R345. You have 2 more that are in parallel, the R6, 7, and R8. So you flip those upside down, a 30th and a 15th. Common denominator, flip them back upside down, or right side up, if you will, and that means they work out to 10 ohms. That's step 1 and 2. Step 3 is repeat, if necessary. Well, I now have 3 resistors in series, 8 ohm, 2 ohm, and 10 ohm. So I just add them up, and that adds up to 20 ohms. That is the equivalent resistance of all 8 resistors. And the circuit is equivalent to this circuit, which means we can determine how much current flows in it. I have 100 volts and 20 ohms. Ohm's law says voltage equals current times resistance. So 100 volts is equal to the current, which I don't know, times 20 ohms. So when I do the math, it works out to 5 amps. Okay, so the total current in the system, in the entire circuit, is 5 amps. Now what we have to do is go back to our original circuit, and we're going to fill in this chart where for each of the 8 resistors, we end up calculating the current and the voltage, and we'll have to do this in somewhat different ways. So where do we start? Let's start coming out of the positive side of the battery. That green arrow there just shows the direction of conventional current. Remember that conventional current acts like it's protons moving out of the positive side of the battery. We know it's actually electrons moving out of the negative side of the battery, but it doesn't matter. As long as you're consistent, the math works, all the way through. So we're going to act like it's conventional current. So that first resistor there, I've got a 5 ohm resistor. And I already calculated that there's 100 amps worth of current coming out of that battery and going through the circuit. So I can figure out the voltage drop across the first resistor. I know that the current, if you look on the chart down there, the current is 5 amps and the resistance is 5 ohms. V is equal to IR, so the voltage is just 5 amps times 5 ohms is 25 volts. Now, that means if you were to put a meter on either end of R1, you would measure a voltage of 25 volts. Difference between one side and the other. If I looked at where this blue arrow was and measured the voltage of that point, it would be 75 volts. The reason is it started off at 100 volts, it dropped by 25 when it went across 1, and it's now at 75 volts. We'll need to remember that here in just a little bit. But now we can do resistor number 2. It's the same deal. I still have 5 amps worth of current going into resistor number 2. There's nowhere for that current to go. Remember, current is the amount of coulombs passing by a location in a second. You could also say that was the number of electrons, or in this case protons, passing by in a second. So we know the current, we know the resistance, V equals IR, so we can figure out the voltage drop of 15 volts across resistor number 2. Now, so that means if I measure here, on the other side, the left side of the resistor, it's 75 volts. It's dropped by another 15, which means it's now at 60 volts right there. Okay, now that's when things get just a little tricky. If you look at R3, 4, and 5 here, they're in parallel, which means when the current gets to that intersection, it can split and go in any of 3 directions. And some of it does go through R3, some through R4, and some through R5. And we have to figure out how much goes through each. Well, easiest way to do that is to replace those 3 resistors with their equivalent resistor. You remember a while ago when we were looking for equivalent resistance, we found that it was 2 ohms was the equivalent of those 3, 4, and 5. So how much current is going into that equivalent resistor? Well, it's still got to be 5 amps because there's all these are in series now. So the current goes through R1, and goes through R2, and now it goes through R3, 4, 5. So if we know the current going through it at 5 amps and the equivalent resistance of 2, we can then calculate that the voltage drop, again, since V equals IR, we don't know the voltage, but we know the current is 5 amps, and the resistance equivalent resistance is 2 ohms. Therefore, 5 times 2 is 10 volts. That means that the voltage drop across both the equivalent resistor and all 3 of the actual resistors is going to be 10 volts. Once we know that, we can figure out how much current goes through each one. So, for example, for R3, I've got 10 volts and 6 ohms, and voltage equals current times resistance. So it's 10 volts over 6 ohms would equal the current. And that would be 1 2/3 an amp. If you just do that on a calculator, you'll see that works out that way. Same thing for R4. It's 10 volts divided by 12 ohms, which is 5/6 of an amp. And then for R5, it's 10 over 4, which is 2.5 amps. Now, if you were to add all 3 of those numbers up, the current going through R3, R4, and R5, you're going to get that it equals 5 amps, as it should, because the ohms the current that is coming into this intersection is splitting up, and it reconvenes down here, so it's got to still equal 5 when it gets out of there. Okay, we're almost home free. We now have 5 amps worth of current coming out of here, and the voltage has now dropped to, at this point, it's now equal to 50 volts. That is, it dropped by 25 going across the first, by 15 going across the second, by 10 going across any of 3, 4, and 5. So that means the voltage right here is 50 volts above 0. Okay, now we're going to do with these 2 resistors that are in series plus in parallel with this other one, R8, we're going to do the same thing we did. We're going to find the equivalent resistance. You remember it was 10 ohms. The current going through there is going to be 5 amps. That means that we can know that the equivalent drop across here, 10 ohms times 5 amps is 50 volts, and it was 50 right here, so you would expect it to drop by 50 to be 0, because it's got to be 0 by the time it gets back to the negative side of the battery. Splitting those back up into their original resistors, that means that I can know on R8 here, I can know the voltage drop is 50 volts across it. The voltage drop is also 50 if you go from this side of R7 to that side of R6, but we can't do that in one easy step, but we can for R8. A voltage drop of 50 volts and a resistance of 50 ohms means the current will be 50 fifteenths, which I reduced to 3 1/3 amp. Now, if 3 1/3 amps are going through R8 and there's a total of 5 going through here, that means over here where they split up, there must be 1 2/3 going through 7 and 6. And so we can do that just by knowing that the current is going to all add up to 5 amps. Now we have to see what the voltage drop is against each of these resistors in series. Well, I've got on R6, I've got 25 volts and a current of 1 2/3 amp. On R7, I got 5 ohms. I'm sorry, back here I said 25 volts. I'm at 25 ohms. Let me start that again. For R6, I can figure out the voltage drop because I know the current is 1 2/3 and the resistance is 25 ohms. For R7, current is 1 2/3, resistance is 5 ohms. So that means just doing Ohm's law, V equals IR, I find that the voltage drop is 41 2/3 volts across R6, and then across R7 it's 8 1/3. Now if you were to add up these 2 voltage drops, which would mean the drop here, the voltage is 50, when you get to R7 it's dropped by 8 1/3 to 41 2/3, and when you cross over R6, it's now gone to 0, as it should, because the voltage has to be 0 by the time it gets to the negative side of the resistor. So that's pretty much the whole shooting match with how you figure out resistance, current, and voltage. There's a couple other things you need to point out, or I would like to point out. The voltage right here is 100 volts coming out of the positive side of the battery. Once it's crossed over the R1, the 5 ohm resistor, you'll notice that it's dropped by 25 volts, which makes it 75. When it crosses over R2, it drops by another 15, makes it 60. When it crosses over any of R3, R4, and R5, it's going to drop by another 10, which is going to make it 50. And of course, that'll be true here and here. And then as it drops across the 7, it goes down to 41 2/3. As it drops across number 6, it goes down by the remainder of that so that it gets down to 0. So you can kind of watch what the potential is, the voltage, at any point in the circuit. Other thing I need to point out is, notice here, as the current splits across R3, R4, and R5, that if I add those numbers up, and you can do that on your calculator, or you can say 1 2/3 is really 1 4/6. So 1 4/6 plus 5/6 is 9/6. 1 9/6, which is 2.5. 2.5 plus 2.5 is 5 amps. So anyway, you just need to know that all that math works out, and you may be required to reproduce something like this. One last thing. I said we were going to figure out what the power was consumed in each of these. We haven't done that yet. Let's look at the power in the entire circuit first. The power you can get it in any of 3 ways. You remember Joule's law says that power is current squared times R, or voltage squared divided by R, or current times voltage. All of those are equivalent. That said, let's just do it here in our heads. Let's use I times V, because we can do that in our heads. Current is 5, voltage is 100. That means it's 500 watts is dissipated in this circuit. That's through the equivalent circuit, and that means we'll add up all the power dissipated here, and it should add up to that same thing. So I'm not going to go through the circuit with that, but just know that for each one of these things, we apply, I will say power equals current times voltage. So for R1, it'd be 5 amps times 25 volts. I could have used any of those formulas, but when I do, I get these numbers. If you add those numbers up, then you will find that they add up to 500 watts, which is as it should be. That's really as complicated as it's going to be. I know there was a lot. There was nothing hard there, but there were a lot of little kind of baby steps. You may want to go back and watch the video again. But you also need to know that there's when you add them up, it gets to 500 watts. That the test is on Tuesday. Thanks. I'll see you all Monday.